Okay, today we're going to be tackling section 3.4, which is titled Velocity and Other Rates of Change. Really, I call this lesson Position, Velocity, Acceleration, because we're going to be talking about those three titles as we get through this lesson. So, your notes today look like this, and we're going to take some pictures down here on this first page. So, underneath summary here, I have a little sentence, and it says, the change in position with respect to time gives velocity. Velocity represents how quickly position is changing. So here's the visual. If you think back to the beginning of chapter 3 when we did our PQ graph, I'm going to kind of model that graph again. So I'm just going to draw a y-axis and an x-axis. And I'm just going to draw that same curve that I did earlier in chapter 3, just something coming through like this. But this time, instead of calling the x-axis, we're actually going to call it the t-axis. And let's just give it the units of hours. And instead of having the y-axis, we're actually going to call this the s of t-axis. This is position. We're going to label that as miles. So this graph is tracking an object's miles over time. Okay, so if we were to pick 2 points on this graph, and if we were to draw a tangent line at one of these points right here, and we wanted to find the slope of that tangent line, then that slope would look something like this, rise over run. The rise would be modeled as miles because it runs parallel with the miles axis, and the run would be hours because it's running parallel with the t-axis. So if the equation y equals s of t is our position equation in miles, then the derivative y prime, which would be s prime of t, would be miles per hour. And we call that velocity, v of t. Okay, so just to review, we grabbed a position graph tracking distance over time. And when we find the slope of the tangent line somewhere on that graph, we end up getting that slope is measured in miles per hour. So, in other words, what we found is that the derivative of the position graph gives us velocity. Okay, let's move on. Now, what happens if we're looking at the change in velocity with respect to time? This is actually going to give us acceleration. Acceleration represents how quickly velocity or directed speed is changing. So my visual for this is pretty much the same as my visual upstairs there, but the units are going to change. So now pretend we're looking at a velocity graph. And we're going to call the x-axis, the t-axis again. We're going to measure that in hours. And we're going to now call the y-axis the velocity axis, which is going to be measured in miles per hour. So now, if we pick a point on this graph, and we draw a tangent line there, the slope of that tangent line, which would be rise over run, would be measured as, the rise would be the same units as the y-axis, miles per hour, and the run would be parallel to the t-axis, so we're going to measure that in hours. So, from up above, if y prime was equal to v of t in miles per hour, then y double prime is going to give us a of t, acceleration, measured in miles per hour per hour, and I'm getting that from this slope right here, miles per hour, which we can also call miles per hour squared. And the reason those units work out is because if I take my miles per hour divided by hours, that would look like this. Miles per hour divided by hours is the same as miles per hour times 1 over hours, which gives me miles over hours squared. So, the order of my derivatives then, at the bottom of the page, goes, when you start with position, s of t, if you take a derivative, you get to velocity, v of t, and if you take the derivative of velocity, you get to acceleration, a of t. Okay, let's flip the page. Just a few notes here to read, starting with speed. Speed's something you've dealt with your whole life. Speed is actually the absolute value of velocity. Speed is always a positive value. Velocity can be positive or negative as it represents directed speed. If velocity is positive, it means an object is moving upward or to the right at a certain speed. If velocity is negative, it means an object is moving downward or to the left at a certain speed. This might be a new word, displacement. Displacement represents how far an object is from its original position. And I have two formulas here for you. Given the position of an object, s of t, over a time interval from A to B, the displacement of that object is position at time B minus position at time A. And also, if you're given the position of an object, s of t, over a time interval A to B, the average velocity of that object is given by s of b minus s of a all over b minus a. And I can give you a visual on that if we draw another graph like so. And we're going to call the x-axis t in hours again. Slide this up a little bit here. And we'll call the y-axis position in miles. If we pick 2 points on the graph, and we draw a secant line connecting them, then the coordinates of the first point might be something like this. A, this would be position at A, so our coordinates could be A, comma, position at A, and this would be B, this would be position at B, so B, position at B, B, S of B. So our final slope then, or our average velocity, is going to be y2, s of b, minus y1, s of a, all over x sub 2, b, minus x sub 1a. The change in position, of course, is in miles, then the change in time is hours. So that would be your average velocity. And then at the bottom here, given the position of an object, s of t, at a specific time, t equals a, if we want the instantaneous velocity, that's just going to be the derivative, s prime of a. So if I want the instantaneous velocity, not the average, then I have to do the slope of the tangent line, not the slope of the secant line. So the slope of the secant line is to average velocity, as the slope of the tangent line is to instantaneous velocity. The next page is just for you to read. I'd like you to take some time and read this position, velocity, acceleration information. I think it'll help to summarize what we're doing. Same with the next page. You can read that. It's just a little blurb on average versus instantaneous speed. So please read that as well. But we'll go on now to the examples. I have 2 examples here which will help you get through your homework tonight. Okay, so example. So let's start with example 1. It says a particle moves along the line so that its position at any time t greater than or equal to 0 is given by the function s of t equals t squared minus 3t plus 2, where s is measured in meters and t is measured in seconds. Find the displacement during the first 5 seconds. Okay, so we're just going to use that formula from the other page. So displacement is going to be position at end time minus position at start time. So if I'm finding the displacement during the first 5 seconds, 5 seconds would be the end time and 0 seconds would be the start time. So I'm just going to plug 5 into my S equation up here, and then I'm going to plug 0 in, and I'm going to subtract. So position at 5 would be 5 to the second power minus 3 times 5 plus 2 minus, now I'm going to plug in 0, 0 to the second power minus 3 times 0 plus 2. And when I do that math, I'm going to get 12 for s of 5, and I'm going to get 2 for s of 0. So my final answer, my displacement, will be 10 meters. So during the first 5 seconds, the particle moved 10 meters. Okay. Find the average velocity during the first 5 seconds. Okay, that's a different formula. Average velocity is position at end time minus position at start time divided by end time minus start time. So I'm not going to go through all this math again. I already know that position at 5 minus position at 0 is 10 meters from earlier. So I'm just going to take 10 meters divided by 5 minus 0 is just going to be 5 seconds. And when I do the division there, I'm just going to get 2 meters per second. So the average velocity of the particle during the first 5 seconds was 2 meters per second. Part C, find the instantaneous velocity when t equals 4 seconds. Instantaneous velocity is derivative of position. Velocity is the derivative of position. So I'm going to take s, so if s of t from above equals t squared minus 3t plus 2, then v of t is going to be the derivative of s. So I'm going to take the derivative of this, which is going to be 2t minus 3. Now that I have that derivative, I'm just going to plug t equals 4 in. So v of 4 is going to equal 2 times 4 minus 3, which is 5 meters per second. So that's going to be my instantaneous velocity. Part D says, find the acceleration when t equals 4. Well, acceleration is the derivative of velocity. So I'm going to bring velocity down here. V of t equals 2t minus 3. And I'm going to find the derivative of that, which is going to give me acceleration. Well, the derivative of 2t minus 3 is 2. And since that's a constant, when I go to plug 4 into that, a of 4 is still just going to be 2. And my units for acceleration are meters per second squared. Okay. Letter E. At what values of t does the particle change direction? A particle is going to change direction when its velocity is 0. Think about it. If something's moving, the only way it's going to change its direction if it stops, turns around, and moves the other direction. So to find the value of t where the particle changes direction, I'm just going to set velocity equal to 0. So grabbing velocity from part C, 2t minus 3, I'm just going to set 2t minus 3 equal to 0 and solve. If I add 3, I'm going to have 2t equals 3. and divide by 2, so t is just going to equal 3/2 or 1.5 seconds. That's when my particle is going to change direction. Okay, number 2. A rock thrown vertically upward from the surface of the moon reaches a height of s of t equals 24t minus 0.8 t squared meters in t seconds. Find the rock's velocity and acceleration as functions of time. Okay, again, we're given position, so to find velocity, we're just going to take the derivative of position, and to find acceleration, we're just going to take the derivative of velocity. So the derivative of 24t minus 0.8 t squared is just going to be 24 minus 1.6 t. And for acceleration, the derivative here is just going to be negative 1.6. Part B, how long did it take the rock to reach its highest point? Again, an object or a rock is going to reach its highest point when its velocity is 0, because when the velocity is 0, it's going to stop and start to come back down. So I'm going to set velocity, 24 minus 1.6t. I'm going to go ahead and set that equal to 0. I'm going to add 1.6t to the other side and divide by 1.6. So t is going to equal 15 seconds. So it's going to take the rock 15 seconds to reach its highest point. And then finally, how high did that rock go? Well, if the rock is at its highest point at 15 seconds, then all we have to do is plug 15 seconds into position up here, and that'll tell us how high the rock went. So position at 15 seconds is going to be 24 times 15 minus 0.8 times 15 squared, and that is going to be 180 meters. Okay, so this is going to end this video, and we're going to stop here and do homework it's going to be 10 multiple choice questions, just working with problems like this. Okay, thanks.